Good morning, good afternoon, and good evening. Hope that you are all doing well and staying safe. Here is Mariam Shref, a senior petroleum engineering student at the Lebanese American University. Welcome to the second lecture of our online course, Applications of AI in Petroleum Engineering, presented by a distinguished guest speaker, Dr. Ahmed Farid Ibrahim. Dr. Ibrahim is an assistant professor at the Department of Petroleum Engineering at King Fahd University of Petroleum and Minerals since January 2021. He has worked as a teaching assistant at the Department of Petroleum Engineering at Cairo University for 3 years. Moreover, he has more than 10 years of diversified international experience, including working for Advantech International Company as a geomechanical engineer and Apache's North America Unconventional Resources region as a senior reservoir engineer. Dr. Ibrahim earned his PhD in December 2017 from Texas A&M University. Finally, his research interests include reservoir modeling and simulation for conventional and unconventional resource reservoirs, production and well performance analysis, shale gas and oil resource assessment and characterization, CO2 sequestration, and AI applications in reservoir engineering. Welcome, Dr. Ibrahim, and thank you for joining us. Please note that the deadline for the first quiz posted on Google Classroom is tomorrow, September 14. And on a final note, if you have any question related to the technical content of the presentation, please feel free to drop it down in the Q&A section. Without any further ado, Dr. Ibrahim, the mic is yours.
Thank you, Mariam, so much. Assalamu alaikum, everyone. Good morning, good afternoon. Thank you for attending the webinar today. Inshallah, I'll continue this webinar about the application of artificial intelligence or machine learning in petroleum engineering. So last time, just to recall from what we did last time, I gave introduction about the different categories of the machine learning, and we said there is supervised machine learning and unsupervised machine learning. The in the unsupervised machine learning, we basically feed the model or the machine learning a set of data, and then the machine learning try to make some clustering on this one here based on the features of it. But in the supervised learning, what we do here is we give the algorithm a data set with a correct answer. We give the machine the data set with a correct answer. And so we basically, for example, if we want for the common example that I gave to you last time, I'm predicting the permeability, for example, as a function of the porosity, the gamma ray, and so on. So what I'm giving to the model, I'm giving it a data set of permeability, which is our output, and the other inputs, okay, with a set of data. And then the model start to train itself based on this data. So later on in the future, when I give the model the input data, which is the porosity and gamma ray, it will be able to predict the permeability. So this is the main difference between the supervised and the unsupervised machine learning. Then we said that the supervised machine learning can be used to solve two common problems. The first one is the regression problem. And in the regression problem, we are predicting a continuous value for the output, meaning similar to this example here, we are predicting continuous value for the permeability. So the permeability can be 0.1, 0.11, 0.01, any value for the permeability between a minimum and the maximum. So let's say I get the model to be trained on a permeability range from 0.1 millidarcy up to 100 millidarcy. So our permeability can be any value in between. The second problem for the supervised machine learning is the classification problem. So in this one here, our output or our prediction is a discrete values. Discrete values just mean it is black or white, 0 or 1. And I give an example for this one here, which is the lithology prediction of the formation. Okay, so if I give the machine for the training, for example, instead of the permeability here, I give it the formation. It is a sandstone, it is a sandstone, or it is a limestone. And against this one here, I give it any other input. This input can be the front wheel logs. Okay, so the output for the machine learning can be sandstone or limestone, nothing in between. So this is the meaning of discrete value. So we have two different machine learning, supervised and unsupervised. The supervised one is the most common one that I saw, yani. And the supervised can be used to solve two problems. The first one is a regression, where we can predict a continuous value for the output, or a classification problem that we can use to have a discrete value, white or black. And then also I show this flow chart here for the to build a machine learning module. So we started with this one here by collecting the data, and then we do cleaning, transformation, classification. We did this one here in order to remove any outlier, transformation in order to increase the correlation coefficient between the input and the output in order to improve the model performance, and the classification if the data can be classified into a certain category, similar to what I said before, like if in like beta oil, for example, oil formation volume factor, if you have a data set, try to classify it to different problems, because if we have a different trends in order to increase the correlation coefficient for each problem. Then the next step is the model development. The model development it's started by randomly splitting the data into testing and training. Then the model uses the training data in order to teach itself, in order to train, okay, to build a knowledge, okay, in the model, and then use this trained one in order to predict later on. So how to satisfy, like how to make sure that the model is already trained well enough to be used on the future. We do something called the performance evaluation. We want to evaluate the performance of the trained model. Once we are satisfied with the performance of the training, we have a validation test, a validation set, or a testing set. We test the model again using data that was not used on the training. And then we check this one here also by making the model evaluation technique. If we are satisfied, that's it. We can use this one here later on to predict any future data. If not, that means we have something wrong with splitting between the testing and the training. So today, inshallah, I'm gonna talk about the model evaluation, how to evaluate the model performance even after the training or after the testing or the validation. So let's start. What is the model evaluation? What I want to answer. So I want to answer, how well is my model doing? Like, is my model is doing well? It can be used? Is it the performance for the model is good enough or not? Can I apply this model to another data? So after I trained it and then I tested, can I use this one here to predict any data that was not used to build the model? Will training my model on more data can improve its performance? Like if I train the model in after I split the data, as I said before, we usually split it to 70% training, 30% testing. If I split it differently, will this affect the performance? Will this affect the performance of the model if I increase it to 80% training and 20% of the data used for testing? And the last one here, do I need to include or exclude any other features to improve the performance of the model? Like for the prediction of the permeability, for example, as I said here, you can get it as a function of gamma ray and the porosity. If I added more feature, is this one will improve the performance? If I added the grain density or the bulk density in the as the input for the model, will this improve the performance or not? Another example in the lithology, if I have so many well logs, if I included all of it how gonna be the performance if I take one of the model or one of the gamma ray from the input, how this will affect my performance. So this is what we're gonna answer inshallah today from the model evaluation section. We'll do it based on the class of the supervised or based on the problem. We said at the beginning we have two different problems to be solved by the supervised machine learning. The first one is the regression problem. The second one is the classification. For the regression problem, we predict a continuous value. So there is no correct or incorrect. So the value that we predict, it's not like black and white. That means if we're predicting permeability, for example, if the actual permeability is 110 millidarcy and we predicted it 108, okay, it's pretty good, it's not bad. So it's not wrong. The meaning of this one here, it is not wrong. Even it is not the same value as the output. It's 110 millidarcy and this one here is 108 millidarcy, for example. So it is still, our model is doing very good job. Okay, comparing to the classification, if I want to predict the formation, it is a sandstone and he gave it to me as a limestone, that's completely wrong. So in the classification problem, it is either correct or incorrect. But for the regression problem, it can be good, can be pretty good, can be excellent, can be bad, and so on. So in the regression problem, we are testing how close your prediction against the actual value. We are trying to predict how the output from your model close to the actual value. So we do this evaluation here for the training set and later on for the testing set. The first thing of the evaluation is the visualization. Basically, it's just visualization evaluation for the results by the cross plot. So the first thing here is a cross plot. You are plotting the actual data versus the predicted data. And if you use the same scale in the X and the same scale in the Y, so if your model is accurate, your dots here, your point here should be aligned with the 45-degree line. That means if you have a value, if you have the actual value is 1, for example, you can see here the predicted one is also 1. So the first way of classification of evaluation is the result of is the visualization using the cross plot. And in the cross plot, we plot the actual versus the predicted data, and we see how this one here is aligned to the 45-degree. So if your data is scattered like that, away from the 45-degree, that means your model is not working well. You need to make more adjustment. You need to make more changes on the model or in the features in order to improve the performance. The second way is the trend, to plot your data against each other. Okay, so you are plotting. Okay, so for example, this one here, you are plotting the actual, which is in the blue line, versus the predicted, which is the red. And you can see here that your data, okay, the predicted data is match, which is we're calling it here the history match. The predicted data here is perfectly match the actual data. That means we were able to predict the actual data. For example, if this one here, for example, is a well logging, I'm predicting the gamma ray, for example, versus the depths. So at any depths here, you can easily use the machine learning tool to predict your gamma ray, and it will give you a very good results. So this is one here for the visualization. This one here cross plot, if it's aligned to the 45-degree, that means we have a good results. If it is scattered away from the 45-degree line, that means the model is not doing well. In the matching, if we have a good match, that means our machine learning model is working well. If you have mismatch here, see, like the predicted model slightly overestimate the gamma ray, give higher value for this one here. That's mean here it is less matching. So what if we want to have quantification for the number of the, in order to evaluate the model, to say, like if we are 1, that's perfect. If it's 0, that's not good. The first one here is the residual analysis. So the residual analysis is basically the actual minus the predicted value. The actual minus the predicted value. So for example, if I have the gamma ray here, this is my actual value, like let's say 200 API, and the predicted gamma ray here is 205. So our residual is basically the 205, or the 200 minus the 205, that's minus 5. So this is basically the residual. In order to test the model, if the model is working well or not, or the regression is working well, very good or not, first is compare the absolute value of the residual. So see this one here, what is the maximum and the minimum residuals. If this one here is a high number, that means the difference between the actual and the predicted value is too big. That means there is the performance of the model is not good. So this is the first thing, is the absolute value for the residual. Second, the distribution of the residual. See how the residual is doing. So in order to judge if the regression is good or not, if the model was able to have a good regression along the values of the property, like for example, the property changed from 0 to 0.4, for example, here. I want to make sure that the model was able to make a good regression along the range of the property. So first, the absolute here to judge if the model is working good or not. In order to judge if the regression inside the model is good or not, we see the distribution. The distribution of the error or the residual should be follow a normal distribution. Normal distribution with mean of 0, and then to the right hand side and the left hand side is almost the same distribution. So most of your data point is almost 0. That means it's very good accuracy, very high accuracy between the actual and the predicted data. So this is the first thing, the residual analysis. We calculate the residual, check the absolute value for it. If it's not high, so if it's not high relatively, that means it is good. And then compare, check the distribution of your residual. If it is around the 0, that means you have a good regression. So if you have like your distribution like that, okay, and this is your 0 point, that means your model mismatch all the property in one side. Meaning, like for example, let's say your data scattered like that, and that means here that the model was not able to predict the property at value less than 0.2. So you go back and check what happened to your model at this range from 0, for example, to 0.2. Okay, if you have something like this, meaning like you may need to make some transformation in your features. Maybe you need to make some transformation in the output. You use log transformation instead of using the actual value in order to give the model to make the regression based on the importance, not based on the not based on the size of the data or the scale of the data. So the importance of the residual, absolute, and the distribution. The second thing is the goodness of fit. Is this model was able to fit the data well or not? And in this one here, we use R square. R square explain to what extent the variance of one variable explains the variance of the second variables. Meaning, like if you have, like this is your actual, if this is your actual data and this is your predicted data, for example, the change in this one here, how the change in this one here can be reflected in the actual in the predicted one, and the R squared can be calculated using this equation here. 1 minus square root summation of yi, which is the actual, minus the predicted square, divided by summation of yi minus the average of, which is the mean of the data, to the power of 2. Another one to check the goodness of fit, to see how the data fit to each other, is the correlation coefficient. So it's basically you take a square root of the r square to calculate the correlation coefficient. Correlation coefficient, so this one here, it varies from 0 to 1. Correlation coefficient, it varies from -1 to 1. But in this case here, it's gonna be from 0 to 1, because we want a linear relationship between the actual and the predicted one, a positive linear relationship between the predicted and the actual. As the actual increase, the predicted value also should increase, and we should try to be near 1. As the r square increases or the correlation coefficient increases, that means our model is doing very good. So an example for this one here, let's clean this one here a little bit. So if you have this different cross plot between the actual and the predicted data, if you come from the left to the right, this one here show very good correlation, very perfect positive correlation between the predicted and the actual one. This means here your model is perfectly able to predict your property from the actual or from the input data. Then for the second one, highly positive correlation, there is a good correlation between the input, between the actual and the predicted model, which is 0.8. That means, yes, your model will be able to predict 80% of the data accurately. And then later on, with the 0.3 or 0, just give us an indication that your model is not working well. Okay, something is wrong. You need to add more features, you need to add more data for the training, and so on. So the first thing to quantify the comparison between the actual and the predicted one is the goodness of fit. First one is the residual, the second one is the goodness of fit. Then we can calculate the error between the actual and the predicted data. How to calculate it, how to quantify the error, okay, between the actual and the predicted one. The first one here, there is so many errors that you can use to calculate to represent the error between the actual and the predicted one. But the more common techniques or the more common parameters that we can use to show the error between the actual and the predicted one, the first one is the mean absolute error or the average absolute error. And it's this one here is basically, it is the absolute value of the residual divided by the number of data points. Okay, so it is the absolute value of the residual in order to just remove the sign effect divided by the number of data points. Mean square error MSE, it's basically yi minus yi, the actual minus the predicted one to the power of 2 divided by n, and then you take average also or mean for the summation. So the MAE, the mean absolute error, sometimes we call it AABE. So this one here can be AABE also, average absolute percent error. So this one here measure the error between the pair of observation expressing the same phenomena. So at the same point, so at the same depth, for example, here you have the actual gamma ray, the predicted gamma ray, and you have the actual and the predicted gamma ray at the same depths. So you are comparing these two here at the same depths, so at the same phenomena, you are comparing this observation, and then you basically take an average dividing by n. Mean square error, it is the same, but instead of using the absolute in order to take care of the sign, we take a square in order to remove it. In addition to using the square here, magnify the effect of the high differences. So let's say if the difference between the actual and the minimum here is like 2 in 1 point, And in another one, the difference is 0.5. So when you take to the power of 2, this will be 4, and this one here will be 0.25. So the MSE here magnifies the differences. So sometimes a square or the square root are used, and sometimes or occasionally the absolute value is used, which is the mean absolute error. This is because when you use the square root, the extreme values, which is this one here, so this one here is the extreme values, the big differences is more influence on the results. So this one here is more influences on the results comparing to the small one, because when we take a square, this one here basically will magnify the error. So when we are trying to optimize the model, we are trying to reduce these differences here. Okay, so this is regarding the how to quantify your model, your error. So the first one is residual. The second one is the goodness of fit using the R square or the R, which is the correlation coefficient. The third one is error. So once we know now we quantify it, we want to know why we have this error. What this error is coming from where? Why this match is not good based on the cross plot. In order to do that, we can go through some of the reasons. The first reason here is the underfitting. Underfitting means your model is not able to capture the changes in your actual data. Your model is basically biased from the actual one. Okay, it's not able to train on the data that is given to it. So a biased model may be observed when trains a model to perform a task without presenting all necessary information. So here, if I want to predict the permeability, okay, and I have, for example, the porosity, I know that the permeability is a function of the porosity, the density of the bulk density, gamma ray for the clay content, but I don't have enough porosity. So I just ignore what I did. I just ignore the porosity. I take the porosity out of the equation. What will happen here? Your model will try to train itself using the gamma ray and the density, but it will not able to capture all the changes because we have one feature that's supposed to be included on the equation and we take it away. So when we see that, so first we evaluate the model, we take a cross plot or matching, then we quantify the error, and the error is big. Then we ask ourselves why this error is big. The error is big can be the first reason is underfitting. So this underfitting can be in the training dataset or the observed dataset. So it is likely happen when you are not using enough features to train the model. So this one here, in order to solve this one here, you need to look in the physical meaning or the physical background for the property. What is the parameters that affecting this one here, and try to include it in your equation. The second problem that can cause an extreme error also is the overfitting problem. So overfitting problem, it is the other way around from the underfitting. So in this case here, when we are trained the model, we have a very complex model that was able to train on each point on the training dataset. So it is capturing all the data point, even the noise. If you have a noise, this one here was able to capture this noise, but not the whole trend. This is not the actual trend. So if you try to use this model to make testing on the testing dataset, so in the testing dataset, the model was not trained on it, you can see that there is a big error between the predicted one and the tested data. So the model has a little training error. So in this one here, how to see this one here, when we are doing the evaluation, you will see that the model will pass the first evaluation, which is evaluating the model performance on the training set. you will see that this one here has very small error. And then when we do the reduction for the testing data set, we see that we have a big error for the prediction data set. At this case here, you can say that your model is overfit or overfit the training data so that he was able to capture all the noise, but not the actual trend. So the actual trend for the red point here can be something very simple like this, something very simple just to capture the trend for the whole data set. And if you look between the black line and the blue line here, yes, the blue line here was able to capture most of the changes in the training and in the prediction dataset. So the first one, the first reason for the for the high uncertainty, sorry, high error in the between the prediction and the between the prediction and the actual sets. The first one is the underfitting problem. The second one is overfitting. Underfitting, your model was not able to fit or to train from the model, from the data, so you have high error in the training and in the testing data set. The second one is the overfitting. Overfitting, your model overtrained on the data set as if it is memorized, this one here. So it captures all the noise in the training data set, but not the actual trends. So the error in the training is very small, but when we are trying to use the model to make a prediction for the testing data set, the error is high. How to solve the problem in each one? For the underfitting, try to add more features, try to add more features on the model in order to predict, to allow the model to train itself from this input data. For the overfitting, remove the noise or remove the features that is not important. So an example for that, like let's see this one here. This model here, we have trained data, which is the red, and the tested data is in the green. When the model was trained, we used this model here, very complex one. The polynomial degree here is 4. Okay, so it was able to capture all the noise, all the points for the training, but when trying to get or to predict the testing data, was not able to capture most of it. The error in the data here, in the testing data, is high. So how to solve this one here is to ignore the unimportant features. Keep the more important features and remove the one that is not important. So basically, we can ignore some of this one here and make the model a little bit more simple in order just to capture the trend for your data, which is something like this. So now our model is more simpler than before, and it was able to capture the trend and a good prediction for the testing and the training dataset. Okay, so this is the second, for the overfitting, how to solve the overfitting. So now your data or your error can be due to underfitting. So your model is very, very simple, like this, was not able to train itself from the actual data, or it is overfitting. The model is very complex that was able to capture even the noise in the training data, but not the actual trend. So how to detect this one here while we are developing the model? We use the learning curve. We use the learning curve in order to know if this model here is going toward overfitting or going toward underfitting. So the learning curve is basically show the error of the model with the time or with the experience, with adding more data to the model to train itself on it, or with the time with more iteration versus the error. So you have the error here, how the error it change with more data or more time with more iteration. So the underfitting can be detected when you see that the error in the training and the validation is almost constant. Whatever you add, like you want to predict the permeability as a function of porosity and the gamma ray. Okay, you are not including the bulk density. You are keeping adding data to the model to train it, but still the error here is still big and it is constant. It's not going down. Okay, that means your model is not able to train or to learn from the data that you are providing. The second one that you can see from the model and judge and say this is underfitting, when your data, your error is keep going down even with too many iterations, even with too many data you are adding for the training or the validation data set. As if your model is keep learning, and it's never stabilized, never stop. That means also here your model is not able, there is like features that this one here is missing. So the underfitting can be detected during the model development procedures by the flat losses, the flat error, regardless the training, or continuous decreasing in the losses is continuous learning even after 1,000 iteration, after 2,000 iteration. Okay, and we still did not finish that training yet. We still have a high error after so many iteration or after adding so many data. So this is for the underfitting. What is about the overfitting? For the overfitting, it's basically your model has very small error for the training. Your model capture all the changes. Okay, capture all the changes in the model. So the error for the training is very small. But for the validation start at a high value, then slightly decrease after that, it increase. Once you add more data, your model is not capturing the trend. So let's say here, this is your training data set, something like this. And then your model is basically, when you trained it, capture all the trends like that. But the one that you are using for testing, which is basically this X is here, once you add more data, the error will increase more and more between the actual and the predicted one. When you see something like this, by adding more data, by doing more iteration here, your training error is going down while your validation is going up. You feel that you have an overfitting problem and you need to solve this one here by removing the unimportant features. So this one here, this learning curve here shows the optimum fit, the good fit between the actual and the predicted data, where your training and your validation error is going down, and after some time it's going to stability. So that means your model now you can use it. You can use it to predict any future problem. So the underfitting and the overfitting is one of the main problem or the common problems that will cause mismatching between the actual and the predicted data, and will give us low R square and high error between the actual and the predicted data. The second thing, the third problem that can cause a mismatch between the actual and the predicted one, when we use unrepresentative data set. So I said before, we have our data set, and then we split this data set, we divide this data set to training and testing. So we make this one here as the training for the training data set, and the second one is for the testing. So maybe the data set that we use for the training is completely different than the testing. So when we are trying to test the model in any of this one here, it gives us a completely error, or a very high error, completely different trend. So the first scenario is when we are using unrepresentative training data set. So in this one here, you will see an improving in the learning curve for the validation and the training both, but the gap between both is high. So the gap between the validation data set and the training data set is high, even with more adding data to both, as both here are not representative to each other. So when you take this one here, when you take the training data set and then you train your model on it, when you train your model on it, this data set was completely different than the testing. So when you are comparing the actual and the predicted one, you will see that there is a big difference between the training and the validation. So the training dataset has two or few examples as compared to the validation dataset. So for example, in this case here, instead of using 70-30%, you trained the model on 50% of the data and you tested it on the 50% of the data set. That means you are missing some features, some changes on your data set that maybe it's here in the testing. So in this case here, you need to change your splitting ratio. And instead of 50-50, make it 60-40 or 70-30 and so on. Another thing, make randomization for your splitting. You cannot don't just use, like for the well logging here, don't use just the depths here. Maybe the gamma ray in this one here is very small, and after some time it's increased. If you use your data, this data here, to train your model, and then you are trying to test the model in this one here, the error in the testing data set will be very high. So the main reason for the this one here is the unrepresentative training data set problem. First, the training data set has too few examples. The amount of it, the number of examples here, observation is very small comparing to the validation data set. Second, the training data set containing features with less variance than the validation data set. So this one here, the gamma ray for it is very small comparing to the gamma ray for the testing data set. So to solve this one here, to solve the unrepresentative training data set, first is make randomization, very good randomization. So you take some samples from here from the training, and you take some samples from here also from the training. So when you are trying to test the model on the gamma ray to predict the gamma ray, it already trained on this range and on this range. So it will be able to give you an accurate values. The second one, in order to make sure that the model already trained itself in a similar example, make sure that the training model, the training dataset is bigger than the testing dataset. The second scenario is unrepresentative validation dataset. And in this case here, you can see that your validation is so simple to be predicted. The validation or the testing dataset is very simple to be predicted comparing to the training here. The training here has high error comparing to the validation. And this happens when we have some information leakage from the training to the testing. When you are doing your splitting your data set, like you have poor sampling or poor splitting. So you have a duplicate observation. Some of it is here, and some of, and the same observation is here. You have it here in the validation. So when you are trying to predict the validation, we already have it here in the training. So it will give you the exact answer. The second reason for the unrepresentative validation dataset, when your validation dataset has here a feature with less variance comparing to the dataset, similar to what I showed you in the on this one here. But here, instead of you're training your model in something like this, and you want to validate it in something like this. So the variance, the change in this one here is so big, while comparing to the change in the parameter on the testing dataset is very small. So in this case here, you're going to have a big error in the training dataset, and you'll see that your validation or your testing is much more less. So if you saw after you developed your model and you found that your testing error is less than less than the training dataset error, that means you need to check your data that you use for the training and the parts that you use for the testing. Okay. So now we did talk about the error, cross plot, visualization, quantify the error. The error now is big. What is the reason for this error here? It can be underfitting, or it can be overfitting. It can be the splitting ratio between the testing and the training data set is not good. Okay, how to solve this one here? How to solve the overfitting and the underfitting one? And I said that in the underfitting, it's meaning there is some features are missing, and in the overfitting there is more features that you added to the model that make it very complex, that was able to predict even the noise in the training data set and completely ignore the main trend for the data. For the underfitting, basically you need to look for more data added to your data and see how the prediction look like, or make some constraint. Like for example, instead of this, I'm gonna predict the permeability. I'm gonna predict the permeability, for example, as a function of porosity and the gamma ray, and I will ignore the density. So this one here will give you underfitting. No, make some constraint. So you said, well, I have the density for my problem for the sandstone, for example. I have the permeability for the, I have the density for the sandstone formation, for example. So I make my constraints that this problem here only will work on sandstone, and then I select the input data as a porosity and gamma ray for the sandstone formation only, in order to predict the permeability of a sandstone only. Okay, so this constraint here may help you to solve the underfitting problem, because you just make a constraint, this one here, to solve only a portion of your data where you don't have the density for the other portion. Okay, so this one here regarding the underfitting. Regarding the overfitting, as I said, in order to solve this problem here, you need to remove some features that is not important and only keep the important one. So how to do that? We do it by the feature selection. The feature selection here is basically based on this one here. We want the smallest number of variables or features or parameters that can be used to fit the data or to have a good regression. Okay, so the best scientific model is the simplest model that explains the observed data. So if I want to predict the permeability, you can predict it from so many gamma logs. You can predict it for, you have so many logs like gamma ray, you have resistivity, you have density, you have neutron porosity, you have sonic, you have other logs. So you can use this logs all left, and you said that I will use this one here to solve or to predict the permeability. But this is too many parameters, too many input. It will make your model very complex. That will lead to the overfitting. So your model should be simple enough and at the same time can able to observe or predict your data. So you need to make a balance between the complexity and the goodness of fit. In order to do that, we have like a rule of thumb, the AIC parameter or criteria. So this one here, we want to minimize it. So it handles the number of data points, the number of the parameters, and the error. So you compare your error. Yes, you want to minimize the error in your data, but at the same time, you don't want to have too many parameters on your data set. An example for that, as I said here, you want to predict the permeability as a function of different logs here. You have gamma ray, you have true resistivity, you have micro resistivity, you have sonic, you have sonic, you have neutron porosity, you have bulk density, and so on. Okay, and now I want to predict the permeability. So I did my model, I run it, and I calculated the error. And this one here, for example, this is the mean square error or the RSS, the square resistance. Sorry, the square residual. If you calculated the AIC criteria using this one here, so you include the number of the parameters, the number of the data point, and the RSS, which is basically the square residual, the summation of a square error or summation of a square residual. You calculate it, and this is the value. Then the next step is try to remove one parameter one at a time, run your model, and calculate your AIC again. So first, for this first step, remove the gamma ray, so you don't have gamma ray here. Put the other parameters here and check your AIC. Your AIC here increase. That means gamma ray is important to be in the input for the prediction. Second one, let's remove the resistivity and return the gamma ray again here. When you put it like that, check your AIC here is 386, slightly increased. That's yes, the resistivity is a little bit important, has some importance to predict the permeability, and so on. Check this one here. When you remove the sonic resistivity delta T, the AIC here gave you 381. This is the lowest AIC criteria. That's mean when you remove your delta T here, it will not affect your output results, and at the same time will give you a good simplicity. So now you decrease the number of your input, but your output as an error is the same, even less. Now after this step here, you know now that your parameter are gamma ray, resistivity, neutron porosity. You excluded this one here and this two parameters here. Let's repeat this one here by removing one of the parameters here. So AIC, it is 381. Now let's remove one by one. Let's remove the gamma ray, resistivity, micro resistivity, and so on. And in this step here, we were able to reduce the AIC criteria a little bit. So that means here your micro resistivity here, micro dense resistivity is not important for the prediction. So you can remove it. And the next step, we repeat this one here by trying to remove the other parameters here. Gamma ray, resistivity, porosity, and so on. You can see that your AIC here, all of it is higher than the 381. That means these parameters here are important to predict your model. So by doing this technique here, you were able to simplify your problem. Instead of predicting the permeability as a function of 7 parameters, now you are predicting your permeability as a function of 5 input only. So the first, simplicity. Second, you are taking care of the overfitting problem. So when you train this model here, it will not predict the noise. As a result, when you do the validation or the testing, your model will be able to predict your actual data. Okay, so this is for the regression problem. So the regression problem, it's a continuous problem. So it can be poor, it can be good, pretty good, excellent. Okay, so in this one here, if for example, your R square is 0.8 or it is 0.9, can you say, yes, your model is very good, you did a great job when you get R square of 0.8 or when it is 0.9? So it depends on your problem. It depends on your problem. Yes, 0.9 is much more important, it's much accurate than 0.8, but it depends on the problem. Like if you, like in the literature, there is no one was predicted the permeability as a function of the porosity, gamma ray, or whatever is the available parameter is. And you got R square of 0.8. That means you did a great job. Now, if you have this properties here from the well logs, for example, you will be able to predict the permeability with 80% accuracy, where before you, there was no one were able to do so. But if already some people has this trial here and their accuracy was 0.8, your job now is to try to increase your accuracy, because the people can predict the permeability now by 80% accuracy. If you can increase your accuracy to 95%, this means you did a great job. Other than that, it is meaningless. So the value of the accuracy here, it should be, for sure, it should be higher than 0.7, for example, 0.75, for example, should be higher than this in order to say, yes, I can predict your property with 75% accuracy, but it's also something relative. Compare it to what is currently in the industry. If there's something that can predict your property with good accuracy, 80%, but what you did, you can predict it, but with more accuracy, that's a great job. If you get it with the same accuracy or less accuracy, that's meaningless. So this is for the regression problem. Regression problem, we saw the error. The reason for the error can be the overfitting, underfitting, or the data set splitting was not representative to the actual problem. And we saw how to solve this one here. Adding more features, removing some features, make randomization in the splitting. The second problem is the classification. So for the classification problem, it is discrete output. So your prediction can be correct or incorrect. You want to predict the lithology of the formation. It is sandstone or limestone. So if you give me a sample, you predicted sandstone, okay, it is correct. You said no, it is limestone, it is incorrect. Okay, so it is white or black. So to classify, to evaluate your model, the first thing to evaluate it, we can use something called the confusion matrix. So the confusion matrix, you have this is your sandstone, for example, and this is the limestone. We said this one here. Your sample is a sandstone. Your sample here is not sandstone. So it is, this one here is sandstone, this one here is not sandstone. Okay, and then we compare between the predicted and the actual samples. This one here, the true negative, means that the non-sandstone one, you were able to predict 48 samples accurately. You give the model 48 samples that is not sandstone, and the model was able to predict that this one here is not sandstone. Similarly, for the true positive here, you give the model 37 sample or a rock sample of sandstone, and the model told you, yes, this one here is a sandstone. So this is the meaning of the true positive. So the diagonal here in the confusion matrix gave you the true label versus the predicted label. The one in the diagonal here gave you the accurate prediction. The one in the diagonal gave you the accurate prediction. The higher the diagonal values, the better the model is. That's mean indicating more accurate prediction. The one in the other direction here, anything other than the diagonal, that means the error in the prediction. So for example, this one here is a false negative. False negative mean you give the model a sandstone sample, but the model told you no, it is not sandstone sample. Okay, this is meaning the false negative. The false positive here, your sample, actual sample, you give the model a non-sandstone formation, non-sandstone cores, and the model told you it is a sandstone, so he predicted it wrong. So this is the definition of the confusion matrix. In order to quantify this one here, in order to make it in a number instead of just a visualization here, we calculate something called the accuracy of your model. So the accuracy is basically the number of the correct prediction, which is in the diagonal, divided by the total number of the point. You used the model to predict 100 sample, and then he got 90% of the samples is correct. Either it is non-sandstone or sandstone. That means the accuracy of your model is 90%. So this shape here is for the like if you have only sandstone or non-sandstone, or it can be with many other classes like sandstone, limestone, clays, dolomite. Similarly, the one in the diagonal here gave you the accuracy. That means this is the accurate values. Anything else below the diagonal or above the diagonal, this is the mismatching between the model and the actual data. Plus the accuracy, there is other two parameters here, something called the precision and the recall. So the precision is the fraction of the relevant examples, the true positive one here, among all the examples which you are predicted to belong a certain class. So it is basically tell you the number of accurate predicted sandstone. Like you give the model a certain set of data, and then he predicted 50% of this data to be sandstone. Let's say instead of 50%, predicted 50 sample of this one here is a sandstone. So the precision is basically the accurate prediction in this 50. So the accurate one is this one here was 46. That means your precision is basically 46 divided by 50. So this one here gave you the accuracy in the predicted sample. The accuracy in the predicted sample. So in this one here, when you predicted 50 of it as a sandstone, but only 46 of this one here is actually sandstone. That means your error here is 4 divided by 50. The second one here is the recall. This one here focus on what you are feeding the model. So the recall here is basically the true positive also, but divided by what you actually give to the model. For example, you give the model 50 sample, and this 50 sample, all of it is sandstone. What the model did, it's basically predicted that 46% or 46 of the samples is sandstone and the 4 is non-sandstone. That means the error in this one here is 46 divided by 50 also. Okay, so this one here, focus on the predicted one, from predicted point of view. This one here, focus on the actual, what are you feeding the model. Okay, so this is basically the how to evaluate a classification problem. So the classification problem here is so simple, using confusion matrix, and also based on the accuracy. Here is 90%. Okay, is 90% is good enough? Is on also what the people did before you. Like if you use, for example, the drilling to classify the lithology to sandstone formation. Okay, no one did this one before. So if you did, you were able to predict the lithology of the formation from this inputs here by around 80% accuracy, that's okay. But if some people already did this one here and you got the accuracy of 80%, your job here is to increase the performance or increase the accuracy of the model. So this is the evaluation for evaluation of the machine learning model, and inshallah for the next webinar I will give an example for the production engineering, reservoir engineering, and the drilling application. So that's it for today, and I will be happy to answer your questions.
Thank you, Dr. Ibrahim, for this well-explained lecture. Now we'll be addressing some questions from the attendees. The first question is that what does P in the equation of AIC represents?
This one here, P here is a number of parameters, number of features. So here, for example, in this example here, B is 1, 2, 3, 4, 5, 6, 7. So here I have 7 parameters or 7 input. I'm giving it as an input for the model. So here is 7. And then when we excluded one of the sample, which is the DT, now it is 6. Then when we excluded this one here, now it is 5. So B is basically the number of inputs. Okay.
That what is the most utilized metrics to evaluate your machine learning algorithm?
So it depends on the problem. So if it's classification problem, this one here is very common one, which is the confusion matrix. This one is a very common one in order to give you a good indication at the beginning to the accuracy of your model. And this one here also is just quantification for this one here. The precision and the recalling is important to have these two here if you have the distribution of your sample is not the same. And for example, you have 100 sample, only 10% of this sample here is shale, and you want to predict this one here. So it's important to have this one precision and the recall on your in your evaluation in order to make sure that, like the 10 shale sample, you predicted 5%, like 5 sample is non-shale and the 5 is shale. Okay, so in this one here you will see that the recall here is 50%, which is very low. That means you are not able to predict this one. However, in this one here, if you just depend on this one here, the accuracy will be maybe 90%. 5%, 5 sample was you predicted from the shale was wrong, but the rest was right. And from the sandstone, you were able to predict most of it. So it will give you the accuracy is 90%, which is good. But here, the recall, the minority here, minority give you very high error. So for the classification problem, first start with the confusion matrix. If you are satisfied with it, go ahead, test the precision and the recall. Okay, so this is the main sequence. For the classification problem, as I said, first make the cross plot. This is just visualization, quick one here. So you can see if your data is aligned with the 45 degree, that means your model is good. The same for the matching. Calculate later on the R square and the error. R square and the error. And it depends on the type of the problem. Okay, so error, once you calculate this one here, you will judge your model is good enough or not. Once it is, like, if it's good, that's it. If not, you can go to the other one. What's the reason? If it's overfitting, it's underfitting, and so on. Okay, I hope this answers your question.
Question for today: which method is frequently used to prevent overfitting?
So, from what I saw, like the main technique that can be used to avoid the overfitting one is remove, as I said, make your model a little bit more simple. So remove the non-important features. This is the first thing. Second thing is rely on the model parameter. Like each model, when you are training your model, there is some hyperparameters that you use to optimize your model. Some of these parameters here is responsible for the fitting. So if you increase this parameter, for example, this will make your model overfit your problem. And this parameter here is different from one technique to another. So you just need to play with this one here in order to improve or avoid the overfitting problem. If first, from the data analysis or from the data investigation, try to remove the one with low correlation coefficient, which is not important to your output. Second, start to play with your hyperparameter for the models that you are using. Yes, any other question?
Okay, thank you, Doctor, for your time. I hope you all enjoyed the session today. For those who have missed the lecture or want to rewatch it, the session has been recorded and it will be uploaded soon on Arab Guru's YouTube channel. Now that's all for today. With that, I wish you fruitful learning and have a nice day. See you next Monday.
Thank you so much, and see you inshallah next week. Assalamu alaikum.